Okay, cool. So theoretically, you should already start doing audio. We'll find out. So we already kind of went over, we finished graphing last class, right? We talked about the second derivative test, and we talked about like concavity and how to get that in graphs. Were there any questions for that before we continue? No? All right. If not, what we're going to do is we're going to look at L'Hopital's rule. I think a lot of students like this rule just because it makes limits significantly easier. And basically the rule, there's one thing we have to do, right? So one of the rules we have is we're going to look at a limit like this, right? So we have the limit as x goes to 0 of sine of x over natural log of x. So if I plug in, oh, that's, there should be x on the bottom because natural log of 0 doesn't work. We're going to make this x minus 1 actually. X minus 1. And so if I, x plus 1, sorry. So if we plug in 0 here, yeah? If I were to do the stupid thing, if I plug in 0, I get 0 over 0. Natural log of 1 is just 0. And so I get 0 over 0, and I don't really have any information, right? This is one of the things we saw a few times. And there's other ways to solve this, but we're going to find a nice and easy way to kind of figure out how to solve a problem like this. And this doesn't only happen when we plug in 0, right? Sometimes when we plug in infinity, we'll get the same problem. We'll get a similar problem, right? So if I have like limit as x goes to infinity of x squared over e to the x, if I just plug things in, I would get infinity over infinity, yeah? And so that's another problem. We don't know what this equals. This could equal positive 1. This could equal 0. This could equal infinity. This could equal any number we want, kind of. So like how do we solve a problem like this? And this is where L'Hopital's rule comes in. Basically, whenever we have a limit where we have 0 over 0, or we have plus or minus infinity over infinity, then this limit, what we call it, is an indeterminate form of type, and then we say what type it is. 0 over 0, or plus or minus infinity over infinity. So these limits aren't very easy to solve. We did a couple of them, right? And these are the ones where you have to sit and explain a lot of things. We had to sit and write like whole paragraphs as to how to solve these things. And that's not always fun to do. And so back in 1694, a Swiss mathematician, Johann Bernoulli, introduced a theorem that helps solve these. And basically he introduced the theorem to a French mathematician whose name was Guillaume de L'Hopital. L'Hôpital basically means of the hospital. So for whatever reason, he probably worked in some like hospital circumstance, right? And he actually sold the theorem to them. So L'Hopital bought this theorem from Bernoulli. So this theorem was therefore named after L'Hopital. So he paid the rights to have this theorem. So you know how like some people pay the university money to have their name on a building? Back in the day, the cool thing was to name a theorem after you. Life. Things have changed since then. And I've yet to have someone offer me money to name a theorem after them. But I'm more than willing to accept. Anyway, so what this theorem says, there we go. So what this theorem says is that, so let me highlight this. Yeah, perfect. So here we have L'Hopital's rule. And basically what we're saying is suppose that f and g are differentiable and that g prime of x is not equal to 0. So the derivative is not equal to 0 on some open interval. And we want to suppose that either both of their limits are equal to 0. So notice how we had 0 over 0, right? So we assume both of their limits are equal to 0. Or we assume both of their limits are equal to plus or minus infinity. Then we have that the limit as x goes to a of f of x over g of x is equal to, what we can just do is just take the derivative of the top and the derivative of the bottom, and that'll give us the limit. So basically, if we have 0 over 0, if 0 over 0 or infinity over infinity, then we can do this. So generally when we're proving something like this, you have to first show that you get 0 over 0 or infinity over infinity. So let's look at how this works. I'm going to fix this again. This should be x plus 1. And let's see how this kind of works, right? So we saw earlier that sine of x, the limit as x goes to 0 of sine of x divided by natural log of x plus 1. That gives us 0 divided by 0, which means we can use L'Hopital's rule. So we have that this is 0 over 0. And so we can use L'Hopital's rule. So this makes us happy because that'll make our life easier, because that just means, I guess next page. No, already? Do I have to do it under? Oh, I have room here. So what that means is I can actually apply this, right? So let's apply this. Let's take the derivative. So f prime of x, this is equal to cosine of x, since f of x is equal to sine of x. And then g of x in this case is natural log of x plus 1. And this implies that g prime of x, this is just going to be equal to 1 over x plus 1 times the derivative of the inside, which is just 1. So I'm just going to leave it as 1 over x plus 1. Yeah? And so here we can take the derivative of this. So we have this. And so what does that give us? So we have the limit as x goes to 0 of sine of x over natural log of x plus 1. By L'Hopital's rule, we have that this is equal to limit as x goes to 0 of cosine of x divided by 1 over x plus 1. So what can we do? This comes up on top. So we get limit as x goes to 0 of x plus 1 times cosine of x. So we have limit, so here we can plug in 0. So here we'd have 0 plus 1, cosine of 0. Cosine of 0 is just 1, right? So this is equal to 1. And so we have 1 times 1, which is just 1. And this gives us our solution for this one. Any questions? As you can see, this is fairly nice. It gives us a nice way to kind of view things. And it makes finding derivatives a lot easier, finding limits a lot easier. So let's look at an infinity over infinity example, yeah? It does not work if it's 0 over infinity. So like I said, so there's only two types that this works with, right? It has to be either 0 over 0 or infinity over infinity. In every other case, this does not work. These are the only times we can use this rule. So generally, you're going to want to show, you want to show this first. So let's do this. Show this first. Show first this. Then you can use L'Hopital's rule. If you don't show this, you will lose points, kind of thing, yeah? Any other questions? Yeah. So while people are still copying, so normally if class is canceled and you do have a question like this in the middle, just pause the video. I'll be on Discord and I'll answer you right away. So like this, you can actually continue with your lessons without any interruption, as much as we can. All good? All right, cool. Okay, so let's look at another example. We're going to look at, why is this being weird? This, okay, I'm going to refresh this. There we go. So now we're going to look at the second example, and here we have x squared and e to the x, right? So here, if you notice, if I plugged in infinity, right, I had infinity over infinity. And so I can use L'Hopital's rule for this one. And so we're going to take the derivatives. So what does this equal? So we get f prime of x is equal to 2x. And then g prime of x is equal to e to the x, yeah? So here we have e to the x. And so that means we have limit as x goes to infinity of f of x over g of x is equal to limit as x goes to infinity of 2x over e to the x. So plugging in infinity here, you're going to notice that we haven't done anything. We still have infinity over infinity. But we have infinity over infinity, which means we can use L'Hopital's rule a second time. So this happens sometimes. You have to use L'Hopital's rule multiple times. So basically what we do is we just differentiate both times. So we'll take a second derivative. So we do double prime of x. So this is just going to be equal to 2. If we do the same thing with g double prime, this doesn't change, so we get e to the x. So what we do is, therefore, we can use L'Hopital's rule, and this is going to be equal to limit as x goes to infinity of 2 over e to the x. Now in this case, we know the bottom part goes to infinity, and the top stays constant, and so this is going to equal 0. Since top is constant, since numerator constant, and denominator goes to infinity. Yeah? Any questions for this one? So it has been known that sometimes you do have to do these things 2, 3, 4, 5, etc. times. So just as a heads up, it could be that when you're doing these, if you do find 0 over 0 again or infinity over infinity again, just keep going over L'Hopital's rule until you find some other answer. So let's look at another one. And considering the fears, we're not going to do an exercise, we're not going to necessarily work in pairs, but I am going to still have you work on the problem by yourself for the next 5 minutes or so. So try this problem by yourself, and or if you do want to work with a partner, I'm going to pause the recording for a few seconds. If you were to be home, normally just pause, try it yourself and actually do something. And like test that you're actually understanding it. Because if you're not understanding it, that would be a good time to be like, hey, Aram, I'm not getting it. So I'm going to pause the recording, and I'll give you all about... Alright, so I guess we're going to continue. So theoretically, you should have gotten that this limit is equal to minus 6 square root of 2, unless I screwed up my calculations. But other people are smiling and going crazy, so I assume that's good too. So, how did you get to that answer? That's a good question. Okay, so basically we take the derivatives of both things. So first you have to show that it's 0 over 0, right? So if I plug in 2 to both, so f of 2, this is 4 minus 2, which is 0. And then g of 2 is square root of 2 minus square root of 2 equals 0. So we have that the limit is 0 over 0, so we can use L'Hopital's rule. So then we take the derivative, right? So f prime of x, this is just 2x minus 1. And g prime of x, this is just minus 1 over 2 square root of x. Yeah? Is that okay? Yeah. Yeah? I'm just double checking with the person who asked the question, that's why. It's okay. And so from here, we can take we look at the limits to 2 of 2x minus 1 over minus 1 over 2 square root of x. And so plugging in 2, we would get 4 minus 1 over minus 1 over 2 square root of 2. So we get 3. This I'm going to bring up top times minus 2 square root of 2. So we get minus 6 square root of 2. So that was a super quick way. But yeah, does that kind of help? Good to go? All right. So let's quickly ask, is this on the next page? Yeah. So let's ask, when can we actually use L'Hopital's rule? So here I have 6 different limits. And let's look at when can we actually use it, right? So this first one, what do I have? So I'm taking infinity. and I have 1 over x. So if I plug in infinity, I would get 1 over infinity. So in this case, I cannot use it on this one. So that one's bad. How about the next one? I have infinity. So I have infinity over infinity plus 3. So it's basically infinity over infinity. So this one, I'm good to go. So I can use it on this one. The next one, again, here it's a similar thing, right? So I have infinity on top. I'll get infinity on the bottom. So this is okay. Here, if I plug in 0, I would get e to the 0, which is just 1, and then 0 on the bottom. So again, it's 1 divided by 0. And in this case, we cannot use L'Hopital. So here I'll put 1 over 0. This one was 1 over infinity. Here we have pi minus pi, so we get 0. And then cosine of pi, which is 0 as well. And so in this case, no, cosine of pi is the other side. It's 1. It's minus 1. So this one we can't as well. This is 0 over minus 1. And then finally we have 0 over, maybe I meant cosine. Maybe these should be sines. Did I screw up? They should be sines, I think. Oh well. In this case, again, we can't because we get 0 over 1. I think I meant to put sines there, but I wrote cosine for some reason. Does that kind of help? So like in these cases, we have to make sure that we have either 0 over 0 or infinity over infinity, or else we cannot use L'Hopital's rule. But luckily, we can actually use it for other kind of things. Why is it doing this? This is so weird. This normally doesn't happen. I wonder if it's because it's screen sharing? There we go. So it turns out we can actually exploit this rule for other forms. And we can kind of see this with this one. So we're going to look at the form infinity minus infinity. So this is not 0 over 0 over, nor is it infinity over infinity, but we can kind of change our equation so that it is one of those two forms. And basically, we're going to look at this through an example. And so I'm going to take the limit. I'm going to find the limit of 1 over x sine of x minus 1 over x squared as x is going to 0. So if I were to just plug it in, right, so let's plug it in. Let's go back to black. So if I plug it in, I get 1 over 0 minus 1 over 0. These are technically infinities when we take the limits, right? So this ends up being infinity minus infinity, right? So how do we make this look like either 0 over 0 or infinity over infinity? Those are fractions. We have a fraction minus a fraction, so let's merge the fractions together so we have 1 and see if that kind of helps. So in this case, normally they're fractions, and that's basically what we have to do. So here we're going to try to get the two denominators the same. So here on the left, I'm going to multiply, it looks like we're missing an x, so I'll multiply x over x here. And then here on the right, I'm missing a sine of x, so I'll do sine over x over sine over x. And so we end up getting x minus sine of x over x squared sine of x. This is limit as x goes to 0, and it's equal to that. Is that okay? So here if I plug in 0, I get 0 minus 0 divided by 0. So here I get 0 over 0. And so I can now use L'Hopital's rule. And so I'm going to use it on this. I'm going to take the derivatives of the top and the bottom, and then I can, I'll know the solution to my limit. So here if I take the derivative, my f of x here is x minus sine of x. So f prime of x is equal to 1 minus cosine of x. And then g of x in our case is x squared sine of x. Since that's the denominator. So the derivative is going to be, we're going to use the product rule, right? So we have 2x sine of x, derivative of x squared, times sine of x, and then derivative of sine of x times x squared. So we have x squared cosine of x. Oof, this is disgusting. So what we end up getting is it still going to be like that? Yeah, it's still going to be like that. So if we plug in x goes to 0, we'll end up getting 1 minus 1 on top, and we'll get 1 times 0 plus, 0. So we'll get 0 plus 0 as well. So we'll still get 0 over 0 in this case. So this is still 0 over 0. What's up? No. Yeah. They just canceled?
So their Instagram says, beginning Monday, March 16th, all you hashtag your two classes will move to online format in response to COVID-19.
So starting this Monday?
Yes.
All right. Let me finish this example. We'll quickly talk about that, and then we'll finish up the last few minutes because we're already here. Okay, we're already here, so might as well just finish. Okay, so we have f prime of x is equal to this. So if we were to plug in the limits, we would still get 0 over 0. So that means we're going to have to take the second derivatives. So we're going to do this again. So if we take the second derivatives, and I might not have room for g prime of x, here we'll get minus, so the 1 goes away, cosine becomes minus sine, so the two minuses cancel. So on top we get sine of x. And on the bottom, we get some big, long, complicated thing. I'm not going to write it down because that's really disgusting. Why did I choose this example? Okay, I chose a fun example. So you should try this at home, actually. Like, try to do this derivative because it might be something that appears. So we have like this. And then what this ends up being is 0 over 0 again. You'll have to take the third derivative. And then from there, after the third derivative, you'll find that when we look at this, that we end up getting 1 over 6. So I won't solve it just so that we have enough time to discuss the other things. But it's basically just doing derivatives after derivatives. So it's good practice with derivatives for that. Are there questions for this? Okay. So let me pause this.